In this video, we're going to take a look at the binomial probability distribution. So first we need to look at the definition of what a binomial distribution is. The first condition is that the procedure has to have a fixed number of trials, so you can only do the experiment a fixed number of times. The second condition is that the trials must be independent of one another. In other words, the outcomes of any individual trial doesn't affect the probability in the other trials. So the probability of having a success needs to be the same every single time. The third, each trial must have all outcomes classified into two categories, commonly referred to as success and failure. So there can only be two outcomes. Number 4, the probability of a success remains the same in all trials. Notation for the binomial probability distribution. So S is going to indicate a success, F will be for a failure. The probability of S, we just will use a P to denote, that's the probability of a success. The probability of a failure, we'll just use the letter Q, and that's equal to 1 minus P. N will be the number of trials total. X is a specific number of successes in n trials, so X can be any whole number between 0 and n inclusive. It can be 0 and it can also be n. So X is like the probability, so you're going to find the probability that X is equal to some number or less than some number or greater than some number. N is how many times in total you're going to do the experiment. P again is the probability of a success in one of the n trials. Q is the probability of a failure in one of the n trials. P of X is the probability of getting exactly X successes in n trials. Here we have the binomial formula. You will never need to use this. So don't forget that you will never need to do these by hand. You'll be able to either do them in one of two ways. One would be to use a table that I would provide for you during an exam. The second way would be to use a calculator. So you can do one of those two things in order to calculate these probabilities. I will do one by hand using the formula just because I think it's nice to know where the numbers are coming from, but we'll just do the one. And again, you will never need to use this formula again. The probability of X in n trials is equal to n, and this exclamation point means factorial. So for example, if you want to calculate 6 factorial, then this is 6 times 5 times 4 times 3 times 2 times 1. So you multiply this number times each number down from it down to 1 is how you do a factorial calculation. So 5 factorial would be 5 times 4 times 3 times 2 times 1. So the numerator is n factorial divided by n minus x factorial times x factorial times p raised to the x times q raised to the n minus x. So again, n is your number of trials, x is the number of successes that you have among those n trials, p is the probability of a success, and q is the probability of a failure. So let's take a look at some examples. Example 1, when an adult is randomly selected, this is with replacement, there is a 0.85 probability that this person knows what Twitter is. Suppose that we want to find the probability that exactly 3 of 5 random adults know what Twitter is. Does this procedure result in a binomial distribution? So we need to check those 4 conditions that we looked at the very beginning. So the first one is there a fixed number of trials? And the answer to this is yes, there is a fixed number of trials. So we want to find the exact probability of 3 of 5. So this is the fixed number of trials. Number 2 is, are the trials independent? And the answer to this is yes. So the probability that you will get a success is going to remain the same no matter what. So the probability that the first person selected is going to be that they'll know Twitter is 0.85. And the second person is going to be 0.85 because we're replacing these people. The third condition is that you can only have 2 outcomes. And this is also true. They either know or don't know. What Twitter is. And the fourth and last condition that needs to be met is the probability of a success always the same? And the answer here is yes also. It's 0.85, and it will stay 0.85 no matter what. This does result in a binomial distribution. In the next example, if this procedure does result in a binomial distribution, identify the values of n, x, p, and q. So n, we already said what this was. So in the procedure, it says, suppose that we want to find the probability that exactly 3 out of 5 random adults know what Twitter is. So the total number is 5. That would be n. X, our number of successes, was 3 because we wanted the probability that 3 out of the 5 knew what Twitter was. P, the probability of a success, it was told to us that 0.85, that there's a 0.85 probability that a person knows what Twitter is. And then Q is 1 minus P. So that's 1 minus 0.85. Which is 0.15. In the next example, given that there is a 0.85 probability that a randomly selected adult knows what Twitter is, use the binomial probability formula to find the probability of getting exactly 3 adults who know what Twitter is when 5 adults are randomly selected. So we want to calculate the probability that x is equal to 3. Using our formula. So I'm just going to write the formula down on the side. So the probability that x is equal to x is n factorial divided by n minus x factorial times x factorial times p to the x times q to the n minus x. So that's our formula. N in this case, remember, is 5, so that's going to be 5 factorial divided by n minus x is 5 minus 3 factorial, and then times x factorial, so that would be 3 factorial, times p, that's 0.85, raised to the x, so that would be 3, and then times 0.15 q times n minus x, and n minus x is 2. So you can go ahead. I actually, when I'm doing this by hand, I would just write this out, especially since they're fairly small numbers. So 5 factorial is 5 times 4 times 3 times 2 times 1. A lot of these are going to cancel out. And then this is really 2 factorial, so that would be 2 times 1. And then times 3 factorial, which is 3 times 2 times 1. And then times 0.85 raised to the third times 0.15 squared. So now we can cancel some things. We can cancel the 3 here. We can cancel the 2. 1s you don't need to worry about. And 2 goes into 4 twice. So the only things that we have left are the 2 and the 5 in the numerator. So that would give us 10. So it's 10 times 0.85 cubed times 0.15 squared. So now we can type that into our calculator. 10 times 0.85 cubed times 0.15 squared should give you 0.138. Remember, you always want to round these to 3 significant digits, and in this case that's a total of 3 decimal places. In the next example, 945 couples gave birth to a child, and 879 of those children were girls. In order to determine whether such results can be explained by chance, we need to find the probability of getting 879 girls, or a result at least as extreme as that. Find the probability of at least 879 girls in 945 births, assuming that boys and girls are equally likely. So we're going to have to use our calculator for this. And in order to get to the area where you can do this on your calculator, what you need to push is DISTR. It's short for distribution, and the place where you would find this key, so it's right next to the clear button. You have to push second vars. So vars is short for variables. So to get to this distribution area on your calculator, you have to push second vars, and then after that you would pick binom, and there are 2 different options. There's CDF and there's binom PDF. So the C stands for cumulative. So cumulative means everything up to that value of x. So 0, 1, 2, 3, 4, 5, all the way up to x. Binom PDF is, oops, and I have a D there, should be PDF. This is for a single value of x. So using probability notation, this first one, binom CDF, would calculate the probability that, x is less than or equal to x. And the second one is for calculating the probability that x is equal to little x. So this is less than or equal to the value of x. This one is just equal to the value of x. So because it's always less than, you need to sometimes change the way that you write out your probabilities. So in this example, we want at least 879 girls in 945 births. So what we want to calculate is the probability that x is at least, so it can be equal to, but it could be also bigger than 879. So greater than or equal to 879. But this will only compute less than or equal to. So you need to change this. So it's going to be 1 minus. We want to use the complement. So this is 879 on up. So this would be 1 minus the probability that we're less than 879, and because these are distinct values, that would be x is less than or equal to 878. So, typing this into your calculator, you would do 1 minus, and then you would push second bars, and then scroll down until you get to binom CDF. The n value here is 945. This is the number of trials. The x value is 878. This is your number of successes. And p is equal to 0.5 because boys and girls were considering them to be equally likely. So what you get when you calculate this is 0. Okay, in our last example for this video, based on a recent Harris poll, 60% of adults believe in the devil. Assuming that we randomly select 5 adults, find the probability that exactly 3 of the 5 adults believe in the devil. So there is a binomial table, and if you can use the table, then that's totally fine to use the table if you're comfortable with that. Otherwise, you're always free to use your calculator as well. So I'll do it both ways. Sometimes you get a slightly different number doing it one way versus another. So find the probability that exactly 3 of 5 adults will believe in the devil. So that's the probability that x is equal to 3, because we want exactly 3. And so we're going to use the binom. And this time we want exactly 3, so you want binom PDF. So remember, PDF does for one single value, CDF does for that value on down to 0. So grab your calculator, hit second bars, and then you have to scroll down until you find binom PDF. The number of trials is 5. P is 0.6, and x is 3. And you should get 0.3456. So now we'll do this on using the table. So I'm going to open up a table, and this will be provided for you. You should have it with your textbook as well. Okay, so in your binomial table, you'll see that this very first column is for the values of n. This column is for the values of x, how many successes you had. And then you have various probabilities for p. So along the top, they give you p. And so in our example, we had our n equaled 5, so our number of trials was 5. And our probability p was 0.6. So we want to use this column here. But we only want it for... Okay, so here I have the distribution highlighted. And so again, we had p was equal to 0.6, and we had n was equal to 5. So if we wanted to know the probability of getting exactly 3, we would follow that over, and we see that it's 0.346. Okay, so if we rounded our calculator number to 3 decimal places, they would match exactly. Again, sometimes the table value and the calculator value won't exactly match up. The next one, find the probability that all of the selected adults believe in the devil. So this is the probability that x is equal to 5, because we want to know what the probability of all of them believing in the devil would be. So on your calculator, that would be binom, again this is PDF, because we want exactly 5, all of them. So 5 comma 0.6 comma 5. So again, on your calculator, you're going to want to push second bars to bring up the distribution menu, and then scroll down until you find binom PDF. Our number of trials is 5, our probability is 0.6, and our x value this time, again, is also 5. And so this time we get 0.07776 is what our calculator gives us. And if we go take a look at our table, we'll see that we get the same thing, 0.078. So if we round our calculator value, we would get the same thing that we got from the table. Find the probability that the number of adults who believe in the devil is at least 2. So at least 2, but it could be more. So that would be x is greater than or equal to 2. Remember again that your calculator will only do less than, so we would need to convert this to the complement. So that's going to be 1 minus. The only thing that's not included in greater than or equal to 2 is 0 and 1. So it would be the probability that x is less than or equal to 1. So you could do exactly that calculation on your calculator. Type in 1 minus, push second bars, find the binomial, and this time we want CDF because we want both 0 and 1. And the probability that you should get here is 0.91296. Also remember when you're doing this in your homework or in a quiz, make sure that you're checking those decimal places and that you're giving the correct number of decimal places. A lot of times it's going to be either 3 or 4 decimal places for a probability. Sometimes it can be more, though. It depends on the problem. So again, you could use your table for this. So this would be 1 minus the probability that x is equal to 0 minus the probability that x is equal to 1. Oops, that should be a 1. 1 minus. So 1 minus, go over to our table. 0 is 0.01. 1 is 0.077. And you get 0.913. So we get the same result if we round to 3 decimal places for our calculator option. In example D, if 5 adults are randomly selected, is 2 an unusually high number who believe in the devil? So we want to take a look at the probability that we calculated in example C, and since that's really high, then that tells us that this is not an unusually high number. Remember what we were comparing that to is 0.05, and so if your probability is less than 0.05, then you would say that your number was unusual. If it's greater than 0.05, then we would say that it is usual. That's it for this video. I hope you're having a great day. Thanks.